we have seen the nodalization in the last lecture, and in this lecture we look at one method for triangulation. We mentioned that triangulation is not a trivial thing. This method of advancing print method has been developed in late 70s. It has one attractive feature that it guarantees that no new area that lies outside the boundaries is included in the triangulated computational domain. So, this has that guarantee. One of the conditions that we have said was that there should not be any new area that lies outside the computational domain to be included, and this algorithm guarantees that. The triangulation starts from the boundary and progresses inwards, so that we do not have this problem of including external boundary, and the boundaries of the domain, both internal and external, are segmented into edges which are numbered sequentially in clockwise direction. So, you start with the boundary with one boundary point, and then you move along the segments, boundary segments which you have already identified along the nodes, and put them in a sequential order while going through in a clockwise direction. For all internal points, internal domains, we go in the anti-clockwise direction. At the beginning of the triangulation, the front consists of boundary edges. Starting with an arbitrary edge on the boundary, one finds all the interior and boundary points which lie to the left of this edge and select the one which lies closest to form a triangle with. At this point, the edge which has been joined to the new point is removed from the front, and a new front consisting of the two new edges linked in the counterclockwise manner is created. The process continues with the last of the new edges. All the points to the left of the new edge on the front are checked to see which of them fall on the left side, and the closest one is again taken to make a new triangle. So, the front is again redefined, and then we continue like this. So, let us see what it is by taking a very simple example. You have here a chamfered square, and it has been the boundaries of this have been segmented with these linear segments here, A, B, C, D, E, F, G, and then you have 4 internal nodes I, J, K, H, okay, H, I, J, K. It is just to illustrate the process rather than to generate a grid, which is very good for this. So, if you have this, then how does the advancing print method work to triangulate this particular domain, which consists of this chamfered edge. So, we do not want any joining of K with BC in a way that it goes outside. So, there is a possibility, for example, BHC and BHK to be triangulated. So, we would like to see whether how that kind of thing is avoided in this. So, the we start with edge GA. So, we starting with A, B, BC, CD, EF, GH, FG, GA like this, and so we start with this edge, and then you find all the boundary and interior nodes which lie to the left of this. So, when you are looking at edge GH, this is to the left of this, this is to the left of this, we are going in the counterclockwise direction. So, we are going in this direction. So, this edge, in fact all these edges here lie to the left of this. Now, you say which of these nodes lies closest to GA in such a way that we can make a triangle. So, how do we do that? For example, we take a rope, okay, or a thread, and then we say what is the length of the thread which joins, which goes up to H and then gets back to A. What is the thing if we were to wrap it round this edge, G to I and I to A, G to J and J to A, like that. So, the one which has the least length is the one which is the closest. For example, we can say what is the distance here and what is the distance here, what is the total length, distance plus this distance, total length. So, given 2 points we can find the distance, and from that we can find out what would be the total length if we were to make a connection like this, and the smallest of that will be the point with which we should make a triangle. So, using that kind of criterion we can identify H to be the one which is closest, and we join this, and then we have a triangle that is formed. So, at any point we have the front which is advancing towards those as yet unconnected points. So, when we start out we have a front which consists of AB, BC, CD, DE, EF, FG, GA, that is the front which is propagating inwards all the time. So, once we have identified this H here, then our front now is AB, BC, all this, and from here, here, and then comes back to this. Now, you start at this point here and you see what are the nodes which are to the left of this line. So, this is one, and if you prolong it like this, you can see that this is also to the left of this also to the left of it, and all these others are to the right side of this edge as we go from H towards A. So, out of these 3 points, which one is the one which is closest to this edge? Again we can see that this is the one which is which makes the smallest triangle. So, smallest in the sense of this combined length here, and therefore, we join this and then we create this new triangle. So, the new triangle that is created at each stage is shown in blue color here, and the already created triangles are shown in green color here, and the advancing front is always shown in dark black line here. Okay. So, now we are at this point. So, this is the last edge that we were using. So, again here we see which of those points are, which are the remaining nodes, boundary nodes, which are to the left of this, and we see that this one, this one, this one, this are all available, and we find that this is the one which is closest. So, this time we join it like this, and we have a new front which is going now like this, one new triangle created and 2 old triangles, and now we start with this, and then we find that this is the one which is closest. So, we create this edge, we join this thing here, and then we have a new triangle, 3 old triangles, and now here what are the points which are to the left of this one, these points and this point. Out of this is the one which is closest. So, we create this triangle here, and this is our advancing front like this. So, now we are here, and here we look at all the nodes, and we find that this is the one which is closest to this. We create this triangle, and then we have this, and then at this point we find that this is the new triangle, this is the one which is closest to this, and then we create like this. So, we have a shrinking advancing front here and increasing number of triangulated triangles, and the latest triangle which is created. Now, we were here, and this is advancing front, and we are starting from here, the latest edge to be created, and we find that this is the one which is closest to this. So, we join this to make the new triangle. Now, at this point the front consists of coming here like this, like this, like this, like this, like this, like this, and like this. So, this is the latest edge, and we join this now to make this, and then you have created this edge here, and we join this here to create this, and then we join this one to create this, and then this, and then this. So, we have created triangles making use of all the nodes, because we start with one edge here, and then we complete all the nodes here, and this is the order in which we have created those triangles. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is a very robust method that will be used especially for the desirable feature that you are always looking at points which are inward. So, that means that points which lie outside are not linked to form triangles, and that is one very good feature of this. Okay. It has some one distinct disadvantage that this method in this form does not consider. That is, if you take a quadrilateral ABCD and you want to make triangles out of this, you can think of two different ways of triangulating it. For example, you can join BD and make two triangles, or you can join AC and make two triangles. So, the same 4 points, this can be divided into two triangles like this or like this. Okay. Which of these is more desirable? The one which has less distortion, the one which has all the three sides more closely linked to each other. Okay. The three sides which are roughly of the same size, or with the least aspect ratio. Aspect ratio, you can say, is the maximum side length divided by the minimum side length. Okay. So, if you define it like that, then a distorted triangle will have larger aspect ratio compared to the one which is less distorted. Okay. So, then we can see that now there are two possibilities, one like this and another like this. So, which of them is more desirable is that, for example, if you take these 3 points and you draw a circle which passes through all these points, and if the fourth point is lying outside, then this is good because it is producing two triangles here, and this is almost more equilateral than this. You have a long length here and a short length here. So, this one has, this particular combination results in a high aspect ratio triangle rather than this one. So, in this, even these three triangles, these three sides have much an aspect ratio which lies close to 1 here for this triangle and for this triangle. Whereas, if you make it like this, then you have this length which is much longer than this length. So, you have higher aspect ratio. So, this is not desirable and this is desirable. One methodical way of finding this is that in this desirable way, you have angle A plus angle C is less than 180 degrees. And if you join it like this, angle B and D, which are the other vertices which are not joined together. Okay. Now, here these are greater than 180 degrees. And one other criterion is that if you make a circumcircle passing through these 3 points, then the fourth vertex, which is not part of this joined diagonal here, lies outside, and if that is the case, then you have got good distribution of triangle. Whereas, in this particular case, you draw the circumscribing circle like this, and then you find that this is inside. So, this means that this is not a proper way of joining the triangles. So, a given quadrilateral can be converted into two triangles by joining either the diagonal BD or the diagonal AC. Which of them is gives us triangles with smaller aspect ratio, more uniform size, is a question that needs to be asked, and it is preferred to have triangles with smaller aspect ratio. Okay. So, this particular check does not come into picture in making this in the advancing front method in the triangulation. Okay. So, this is a disadvantageous thing. Any correction of the triangulation is to be done after you have triangulated. So, after you have triangulated, you can look at each triangle and see what is the aspect ratio, and take adjacent triangles and see if there is a better way of doing this triangulation by doing this circumcircle option and see whether some correction can be made after triangulation. But there is a different method of triangulation which is known as the Delaunay triangulation or the Boyer algorithm, which incorporates this checking for the good triangulation of a quadrilateral concept in the way it generates the triangles. In the next lecture, we will look at what that method is and how it works, and we will look at a general description, and we will come back to this and then see how it works in this particular case. Okay. So, thank you.